Welcome to UVU CS3060 Lecture 10.10, where we discuss other issues of virtual memory. So, some things we need to consider. We may want to consider with our virtual memory system prepaging. Prepaging helps us get data into physical memory before it may actually be needed. There's a little bit of prediction going on here. Hopefully, this reduces the large number of page faults that occurs when a process starts up. So the way this happens is we pre-page on process startup some of the pages that a process will need before they are referenced. Now, mind you, if these pages aren't accessed, then we do waste I/O. But if these pages are accessed, it will save us quite a bit. And we can see that there's a calculation here. The cost of S time A saved page faults, because we'll have lots of different page faults. If we can save the cost of those page faults, then we can consume less time trying to run the program as the user's interacting with it. Basically, get all the wait time out of the way before the user expects the program to be interactive. Now, one thing we need to consider is page size when it comes to paging. Page size helps us understand fragmentation, both internal fragmentation as well as external fragmentation. Page table size is a big deal whenever it comes to choosing a page size, because when usually a page table is allocated per page. If you increase the size of your page size, you increase the size of your page table, which means fewer page tables in the long run. And the opposite is true if you decrease the resolution of a system. Sometimes if you have a system with a very high page table, the resolution of those particular pages is too high, and you end up with problems. I/O overhead. How long does it take to load large page tables? Remember that Linux has, or that, I'm sorry, x86 or Intel systems and AMD systems have 4K pages, 2 megabyte pages, and 1 gigabyte page. What is the I/O overhead for a 1 gigabyte page? We also have the number of page faults that a system can have. Usually you have fewer page faults with larger frame sizes. Locality. Remember that locality is important because you have to worry about a process accessing memory that is close to other memory accesses during that process run. Locality tends not to be an issue on large page sizes. And you also have TLB issues that you want to deal with. Pages should always be power of 2. And what we find is that page size tends to be growing over time. 4K was the traditional, but again, like I said, Intel has many different page sizes, and we can see that that number is growing. Now, one thing that we need to concern ourselves with is TLB reach. TLB reach is the total amount of memory that is accessible from TLB hits. Basically, the size of our TLB times page size tells us how much memory can be accessed based on a TLB. So again, if we increase page size, we increase our TLB reach. Ideally, the working set of each process will be stored in the TLB. If the working set is larger than the TLB reach, then we end up with a high degree of page faults. So we can do this by increasing the page size. The problem is we can get more fragmentation as we do this, and we don't want to go through that. Plus also, if we're using 1 gigabyte pages, but we're only loading a 20 kilobyte program, that's a lot of waste. We can also provide different page sizes. And the AMD and Intel systems actually allow this. Your process can allocate pages that are not the traditional page size for the system. You can allocate a page that is a 1 GB page within your process. Now, mind you, you have to have the physical memory to handle that, which can be really, really difficult to do on most systems unless you're a high performance system. But if you know that you're going to use the entire page memory, it will save page table size on, as well as your TLB reach. Now, I want you to consider for a moment what happens to paging whenever you're running something like like this particular loop. So we have a loop here that the outer loop is the J loop, the inner loop is the I loop, and we're accessing things using the I index on the outer index and J on the inner. Now, the memory on most systems these days is done based on what is called row major, meaning that each byte is stored in a row, and then the next row down, or the next increment of this particular row, is appended to the end of that. Well, in this particular loop, what we're doing is we're actually accessing based on column major accessing. So we start with column 0, and then we go to column 1, and then, or no, we go to column, we start with a particular column and then go row by row. The problem is that may span several pages. We can see here in this particular loop, we can have 16,000 page faults with this loop alone. Now note the second loop set here. The second loop set has the outer loop as I instead of J, and has J in the inner loop instead of I, in which case now we're accessing the data sequentially. We're actually going from word to word within this particular particular array, and this will only cause 128 page faults. Now, another issue with paging is I/O interlocked. So sometimes when you're storing data through, or retrieving data for a device, those devices need to have that particular buffer in memory at a physical location. It cannot move. We call locking a set of pages so that it does not move. It cannot be swapped out, cannot be moved. We call this I/O interlock, where where the hardware expects the memory to be in a certain configuration. We have to keep these things locked because we don't know when the drive is going to need that memory. The drive, again, is a separate device from our CPU. So locking this memory is a safe way to verify that that device can access its memory. A program, in order to work with this, needs to pin the memory to those pages. And pinning is a fairly common operation with high performance devices. We see it with storage devices, we see it with GPUs, we also see it with network devices. Where, in order to make sure that memory is accessible to the device, a program must pin that memory to a specific set of frames within physical memory. This brings us to the end of Lecture 10.10, where we talk about other issues of virtual memory.